So welcome everybody. Thank you for joining us. Welcome to Flash Memory Summit. This is one of the first panel discussions we've had here, and hopefully you caught our Hyperscale session just a little while ago. One of the first in our great virtual program we have here in Flash Memory Summit this year. So today on this panel, we especially have our speakers from the last session, and just want to give you a quick introduction of those folks. We have Matt Singer, who is a senior staff hardware engineer with Twitter, and Vineet Parikh, he's also a hardware systems engineer with Facebook. Ross Stenford, hardware systems engineer for storage at Facebook. Lee Pruitt, principal program manager, Microsoft, and also Paul Kaler, storage technologist at HPE. So I have you listed a little bit of what those different topics we spoke on just a little while ago. And I think the first step is really to explain that these guys have a lot of deep experience. I have some details on that, but I can't quite access it right now because I'm sharing my screen. But basically, Ross was a longtime storage engineer doing SSDs and controllers, hard disk drives, small and large companies, CNEX and Sandforest, LSI and Adaptech. Matt, is leading the technical leader for the hardware team at Twitter, and an expert in performance and server architecture. Vineet is with Facebook. He's managing their flash across the hardware fleet in their data centers. Had over a decade experience at Intel in their SSD and their storage group. Lee is a principal hardware program manager, 25 years plus experience in the storage industry, magneto, optical drives, spinning rust, up through flash, and also broad range from mobile to data center, NVMe and UFS. It works a lot in standards, so deep background there. And also Paul's a storage architect in the future server architecture team at HPE. He's responsible for researching, evaluating future storage technologies, defining a server storage strategy for their ProLiant servers, and deep into standards, help drive like U.3 and the E3 drive, as well as working with Lee and Ross on the OCP NVMe SSD spec updates. So very esteemed panel here. We're going to open it up to questions here. That's one of the main reasons we have a panel. Wanted to start us off though, just to get oriented. I have a couple questions. I was watching the presentations myself, and I wanted to just get a little bit more deep into some of what was presented. So first question is really for Ross and Lee, and also Paul. Especially, I have a couple questions. There's two of you, or three of you now, and I'll let you choose which ones you want to answer. So first one, you mentioned in your presentation the new EDSFF E1.S as a form factor of choice for hyperscale systems and the industry. And the industry's now developed a large array of options with E1.S drives in production. What are your expectations for actual system usage and industry volume ramp over the next few years?
Who wants to start?
Lee, do you want to start and I can follow you?
Sure. So there is, E1S, it's a great variant, especially for our compute fleet. It allows us to be very fine-grained on how we apportion storage to the compute nodes, with the ability to not take up large portions of the server with the longer E1L like we do for storage. With that, of course, you can never just have one standard for these things. And so obviously there, as people have seen, there is a plethora of the widths. And specifically the widths are kind of tuned for different use cases. We find the 15 millimeter variant very useful for kind of the power envelopes that we want to see for the E1S drives. So we are pretty bullish on that size, and we'll be pushing that one across our compute fleet as we move forward. Ross?
Thanks. So let me add to what Lee had to say. What's really great about the E1S is the mounting holes for the heat sinks are standardized. So you can have one PCB, one firmware, one ASIC, and put different sizes of heat sinks on that based on, or to meet everybody's needs. For Facebook, we really like the 25 millimeter version of the E1S. The reason for that is it provides very low airflow with high performance and drives very dense solutions. If you look at my presentations, you'll see a whole bunch of pictures of boxes that support E1S in a variety of flavors. And so we see this as the next generation for where storage and hyperscale is headed.
Very good. So do you guys have any feeling for how the industry volume is going to ramp to E1S for your use case? Where do you see the industry? Should we see some uptick in the next year or two of E1S usage?
Yes, absolutely. We're basically over our generation 8 servers will be transitioning from M.2 to E1S over that generation 8 lifetime, and then we want to be exclusively on E1.S in our Gen 9 timeframe.
Okay, very good. Thank you. So second question, OCP NVMe Cloud, the SSD spec. So with future revisions of these specs, do you see any opportunity for coordination? You have really a set of different selected requirements, especially based on industry standards such as NVMe and SNIA. Do you see opportunity for coordination with other industry standards groups, or do you expect the spec to follow a similar model where, as it was first developed, selecting sort of the optimal features and configs of the standards that are developed in those groups?
How do you want to say it? So, yeah, I think one of the great thing about the OCP spec that we've been able to put together so far is it's really, I mean, we call it a specification, but it's really a requirements document. And it's the idea of taking all those other industry specs, PCIe SIG specs, NVMe specs, that sort of thing, as you say, SNIA and that sort of thing, and distilling down to, if something is optional, maybe we need to require it for our use cases. So we're going to put in a requirement to say that that optional command actually has to be implemented. If there are multiple ways of doing things, we're going to say things like, hey, let's do it this way. So it's kind of putting the guardrails on a series of these specs where obviously there's lots of different variants and different ways of putting these things together. And so it kind of regularizes what the SSD vendors have to do for our use cases.
Let me add to that, Lee. This is really a collection of all the standards out there and then putting together all the puzzle pieces. So what do you actually need to build a drive? Many things are optional in many standards, and some things we need, some things we don't. This is a matter of pulling all the different standards together to explain how you put together the puzzle pieces. The stuff that's missing in standards, adding in the glue to hold it all together so that you can have a great device out there to deploy in the fleet.
Yeah, and I think I would just add on to that, some of the best practices we've all learned of deploying flash in such large scale are some other things that we try and put into that. So definitely pointing to all the industry standards that are out there, trying to pick those mandatory commands that we need, and then also giving some hints to suppliers to say, these are other things that we've seen that have had issues in the past. And so really trying to make sure that they understand some of those vaguenesses in the industry specs, how do we specify some of that vagueness out.
Okay, very good. All right, thank you very much. So question for Matt. So Matt, in your presentation, using PM to accelerate tweet search, you showed many different performance improvements and interesting value for hyperscale applications in your experiments with persistent memory. What do you think are the more significant characteristics of persistent memory to provide that benefit? Like, is it the persistence, the lower latency, higher bandwidth at lower power? What are some of the most significant contributors you think to that value?
Thanks, Jonathan. One of the, I mean, all of those are important, but I think one of the big differences is being for applications that need that really high bandwidth that you would get from DRAM. It's the difference in the capacity that you can now put on the memory bus. That's one very important difference. There are going to be, I think, a subset of apps that really benefit from persistence, where you want to be able to restart an application quickly that would want to hydrate or have a very long hydration time. But primarily, I think it's all around latency and capacity if you have a need for one or both of those on your memory bus.
Very good. Yeah, it has so many different characteristics. I think that'll be interesting to see what different applications fit to different characteristics.
Yeah, it's really interesting that for a lot of applications, you really need to rethink how the application is going to work in this space, because as soon as you remove if your bottleneck is capacity, as soon as you remove that, you're going to hit another bottleneck. So you really have to start thinking about the whole way that your application is going to be reshaped once you try to move to persistent memory.
Yeah, very good, very good. All right, and we're going to get to questions in just a little bit, everyone's questions. So Vineet, did want to ask you though, in your talk, you mentioned several different pieces of information that could be really useful, very useful doing debug at scale, but they're not in current standards. So what do you think are the highest priority pieces of information out of these that you expect to be specified in future revisions? And is that going to be specified in the OCP NVMe Cloud SSD spec?
Yeah, thanks, Jonathan, for the question. Yes, that's a pretty interesting question. That's something which we have been continuously working as to what's the right set of information to include to determine whether a device is in a healthy state or not. So if I get to the nutshell of it, today we are heavily reliant on SMART, and we all know probably on this call that really doesn't give us much information about what's going on inside the drive with respect to the health. Telemetry being mostly encoded and encrypted has a long debug turnaround time and just doesn't work at scale. So adding data, which is much more easily visible to both sides, like the host as well as to the device, which can determine if the device is healthy or not, is very important. So one of the examples which I highlight in the presentation, which we've added as part of the OCP spec going forward, is going to be on the latency monitoring. So that's one of the key problems which we see in the fleet when certain devices have a read or a write or a trim, which is probably going to take extremely high latency. We would love to capture that and see what's the occurrence of those and then determine what to do with the device. So, yeah.
Very good. Thank you. Yeah, that's excellent. So now I want to turn it over to more of the attendees, if I can figure out how to grab everybody back in. Here we go. So, and all right. So any questions from the participants? Can you please, let's see. You can write it in the Q&A in the Whova, or you can do this here in the Zoom. Let me see if I can. For some reason, it's minimized and won't come back up.
So Jonathan, there is one in the Q&A right now.
Okay, let's see. So the Q&A, yeah, do you see that one? I can't see that one yet. So can you read that one for me?
Sure.
I would appreciate it.
So from our favorite attendee, Anonymous, with heavy reliance on HDD for bulk storage and hyperscale data centers, what is your opinion of the future of these spinning disks where track and bit dimensions are approaching sub 10 nanometer and below, especially with next gen HAMR, knowing that eventually they will be at a dimension physically not feasible? Somebody wanna? I can certainly talk a lot about that if nobody else wants to start.
Yeah, Lee, maybe start us off and then others have some time to think about it as well.
So yeah, I think if you see my presentation this afternoon, you can have basically a slide, and it shows that the pros for hard drives are cost, and the cons are pretty much everything else, with flash being the other way around. And so we use hard drives because we have to, because just the sheer amount of data that needs to be stored. As the drives are getting denser and denser, the issue becomes one of IOPS scaling. Because we're talking about a mechanical device, They just can't get the IOPS to scale along with the capacity. And at some point you hit an IOPS wall where you can't really service that data on that drive of that capacity. And so with that, there's things like dual actuator or multi-actuator in the future that may help with that. But then of course that adds complexity and cost to the device. So going forward, we do see, we would really love to get to some sort of, fancy, I don't know, fancy is not quite the right word, but basically, how do we get the cost of flash down where we can then start to get into the TCO realm that works to replace hard drives? So we can start to get that flash to move down into cooler and cooler data realms because the cost is coming down. And it doesn't actually have to match the actual cost of the HDDs. It just has to be in a kind of a TCO realm. Maybe 2 to 3x the price of an HDD would be very interesting to be able to start to, reduce the number of spinning devices that we need to buy.
Yeah, that's great. Thank you, Lee. Anyone else?
I'll add that I think that we're seeing more and more applications where we wouldn't be willing to tolerate the access time of HDDs. So I think there's going to be a natural progression towards towards more flash and less HDD for a lot of our use cases, except for the coldest of storage needs. So I think there's going to be a natural, just a natural flow towards more SSD storage.
Got it. Yeah, makes sense. Yeah, there's a growing demand for that. All right. Any other questions? Let's see. Any other in the Q&A? I've been able to pull it up now. My other screen is gone. So the let's see. I can try to unmute the line here. I'll try to unmute it for just a second here. No, I can't do that. So anybody have? Can you raise a hand if you would like to ask a question, and I'll call on you. The participants window. Okay, I have a question from Ahmad Dinesh. Ahmad, hey, this is Jonathan. Let's see, I'll unmute you now. Go ahead.
Hey, Jonathan, how are you? Can you hear me?
Yes.
Perfect. So multi-part question, actually. So is the long-term goal of the NVMe Cloud SSD spec to ultimately have NVMe SSD suppliers that can ensure compliance to that spec? And if so, how does one actually confirm that they're compliant aside from making self-validating claims of their own compliance?
Awesome question. You want to start on that one, Ross?
Sure. So if at a high level, the goal is to reduce industry fragmentation because all the drive vendors, as you know, are struggling with resources and time and aligning things. And the question is, lots of people make lots of claims and what's reality versus what's not. And I think that's also a great opportunity for the market. I know there are a number of people, test vendors, who are actually working on things right now. For example, I'm thinking aloud of what's been said, but UNH has publicly posted their test plan for validating these. Okay, Austin Labs has also mentioned that they are working on things. And I'm sure there are others along with those lines. And I think there's a great opportunity for the industry to innovate to test drives better.
Yeah, I'll kind of echo that, right? I think the point of getting to an open specification or requirements document is that we have the industry, they can see every single requirement that we're putting in there. So all of the third-party test labs, they don't have to even engage with us if they want to go figure out how do we make a test suite that can go and validate that somebody meets all these requirements. They can just look at the actual requirements spec that we have in OCP for NVMe, and they can go through and create a test spec so that then vendors can submit that to them, or they can come back and say, hey, we ran it across this test suite and we got, everything is passing. And so we can validate that very quickly, and it's an open test spec. So it makes it easy to make sure that everything that we want tested is in there in an open way. So I think doing it this way makes the testing and validation much easier for the industry because it's all known exactly what we're asking for.
Right. And then maybe to add to that a little bit in the sense of obviously, vendors have their own testing that they do internally. Now they can, start to leverage the stuff that's being brought up by UNH and Oakgate. And of course, we ourselves have test suites that we're, expanding on and developing all the time. So you could think of that as being kind of that defense in depth to ensure that over the kind of qualification life cycle for that device that we're really, really testing it out to all of those different requirements as we go.
Very good. Thank you. Okay, so I see another question. This is, can you comment for the role of tape, such as LTO for data centers of today and especially the future? That's Turgay Goker. So yeah, what is the future of tape, I guess?
Well, I'll just kick off kind of, everybody thought tape would be dead by now, right? I mean, that prediction's been made over and over again, and we still see tape being used. So, I think that just following that, we certainly see the need for tape in the future. But I think, again, as we see some of the hard drive technologies that were mentioned earlier, like HAMR and other future things that are going to drive that cost down, I think that's going to make the role of tape potentially even less, just like flash, as that cost goes down, it makes the role of hard drives even smaller. So I think it's kind of a diminishing role, but I still see it as a significant role.
Yeah, agreed. I think it's one of those, the amount of data and the temperature of that data have to align with the technology used to store it. And so tape obviously is excellent for very large bulk, very, very cold data. And a lot of the stuff that we see around that is it's all those quarterly reports that are now being archived because they got worked on really hard for a week and the report got made and now it just needs to be stored away because there are retention policies that are required for that sort of data. And so tape is a good candidate for those sorts of things that we expect. It's got to be there just in case, but we expect we'll never actually ever access it. It's that sort of thing. And over time, as tape's role grow, as it shrink, some of the things that are coming up, tape does have issues around its, you have to be very careful on how you store it and the controlled environments that it has to live in, and that sort of thing. And so, you've heard some things. Microsoft's been working very hard on DNA storage. So again, something that's very cold, but has a high durability factor and that sort of thing.
Right. Very good. So let's see. I have a question from Chuck. Hey, Chuck Sobey. Let me take you off mute here. Shoot. There you go. Hey, Chuck, go ahead.
Hey there, Jonathan. Thank you for the great session. Actually, I did not queue up a question, so I don't know how that one got there.
Okay, your hand is raised. That's why I was calling you.
I must have accidentally pushed a button.
Okay, no worries. All right, does
Thanks for
anybody
what
else?
you're doing.
Yeah, no worries. So anyone else have a question? Put you back on mute. All right, any other questions? Oh, here we go. Okay, this is from Turgay again. Go ahead. Hi, Turgay, are you there? Okay, Turgay asked her a question earlier from about the tape. Turgay, can you hear us? Okay, can't hear you. Unfortunately, I can't hear you, Turgay, so please maybe type in the Q&A again, and we'll try there. I have another question from William Chung. With the adoption of OCP Cloud SSD spec, do you see the need for SSD customization reducing in the future?
That's the main goal.
Right, exactly.
That's exactly what we'd like to have happen, is have a high quality device and have everybody aligned of what they need.
You know, we still think that, especially as kind of HPE is joined the fray here to kind of work with the cloud aspects and bringing in some of the enterprise aspects. We know we've definitely seen that there are different requirements between enterprise and cloud, but the vast majority of them are shared. And so that's really kind of why we saw the value in joining, was because we could get to, we think, a unified spec where it would be a similar, you know, one device that may have a couple of settings that change based on the use case it's going into, but it's still, you know, extremely highly leveraged, and maybe it's just a couple of settings in firmware that can change even across the same firmware. So it's definitely our goal to kind of minimize the amount of customization and change, so that to the point earlier about debug and validation testing, you know, the more testing that gets done by multiple people that's actually testing all the same hardware and the same firmware, the more value there is in that.
Very good. All right.
Yes, Paul, we're looking forward to you testing drives and finding problems before we do that we can leverage.
Vice versa. Yeah.
All right. Had another question from Ahmad. Let's see. Okay, Ahmad, you left. Go ahead.
Hi, everyone again. Paul, I think you might have actually answered this as you were answering William's question, actually. It was tied to, you know, as HP and Dell are joining into driving the next generation of that specification, Hyperscale and OEMs typically do have diverging features, you know, in addition to even some firmware features, diagnostics capabilities. And so I understand your kind of growth, you know, we can get to some sort of superset. There'll be configuration options, it sounds like, from what you're describing, to configure it differently depending on the use case. The form factors typically differ quite a bit, though, as well. You know, E1.S being driven a lot by Hyperscale, and now some OEM also driving E1.S. But do you see a convergence in the actual form factors as well? Or is the spec actually, having not read the spec, perhaps you guys can expand, does it drive to very specific form factors and capacity targets for those? Or is it more of a firmware level spec and diagnostics and less about the actual end form factor?
That's a good question, especially for folks that are not familiar with it. It is more of a firmware level spec, right? There are more things than just the firmware requirements in there, but I would say that's the predominant bulk of the spec or requirements documents, is what does the firmware look like, and, you know, can we get to a kind of a unified firmware? So I think that's the majority of it. There are lots of other requirements in there. There are some specific requirements around form factors. So there's some power and performance and other things around form factors as well. So it is a pretty comprehensive spec, covers lots of different things. But I think from a convergence perspective, I think that there will, you know, from a form factor versus just firmware, I think it's easier to get to a firmware convergence where we can maybe have a couple of configuration options that are very quick and easy to change over based on the use case. I think from a form factor perspective, that will likely continue to be diverged. So I think, you know, for instance, we've got to be able to handle 2U servers much more than I think the hyperscale space does. So they're very focused on 1U servers, which I think drives the interest on E1, whereas we're much more focused on E3 as a future form factor, but still getting to leverage a lot of that firmware code, because really when you look at the form factor, it's the same SoC, the same ASIC, be the same firmware across different form factors. So there's still highly leveraged capabilities between that.
Yeah, and I think there is a call out for like E1.S. Like, you know, remember also the earlier stage of this, right? It started with Microsoft and Facebook, especially aligning on here's a common set, and so there's that common set, and then there's a ability to branch out where it needs to branch out only, right? So, you know, Ross or Lee, you comment on that as well, and not just form factor maybe, but it's firmware plus form factor plus other things as well, right?
Right. Go ahead.
There's security. There are many topics that are in common. You know, for form factors, it does list requirements around form factors, but that doesn't limit that those are the only form factors you can use. As a majority of the stuff leverage. The goal here is to find commonality among everybody and drive towards common sets of requirements.
Yep.
Yeah, good. So related question from an anonymous attendee again. What's the key differences between OCP Cloud SSD and generic SSD?
Well, I think the way I would put it is, generic SSDs, if what you're talking about in the question is generic firmware, that's each vendor's kind of implementation of what they think their customers want for firmware. And what we've seen, right, is if you pick any drive, which you wind up getting across the industry, is everybody implements it slightly different. So generic firmware is not implemented the same way across different suppliers. So you wind up getting some features implemented, some features may not be implemented. And so you wind up with kind of a hodgepodge of compatibility issues between those SSDs, depending on what the supplier decided to put in their own generic firmware. Whereas with the OCP NVMe firmware spec, we're really trying to guide everybody to say, here is what we need. So across multiple suppliers, they'll implement it the same way. So we can have great multi-sourcing between suppliers. It's good for assurance of supply. So that's really the biggest difference, is that it would enable us to use this, an SSD from multiple suppliers and not have to worry about compatibility differences between them.
I think kind of to riff on Paul's take there, to go even deeper, generic firmware is almost a oxymoron, unfortunately, because as he says, each vendor does it slightly differently, but then today, before the OCP spec at least, all of us customers each had our own purchase specs, which then called out completely different things for things like, say, telemetry or whatever. So we're all asking for the same things, but we all did it in different ways. And so it becomes kind of this multi-dimensional problem that the guys, the vendors have to kind of have for their firmware and all their different firmware builds for every single customer and that sort of thing. And so that's kind of, we want to get away from that and actually truly have the OCP variant be that generic.
Yeah, makes sense. Okay. It looks like we're getting close to time or a little bit over. So I want to make sure we have two more questions. I'm going to ask these last two as our final questions. One question from Jonathan Hughes. Question regarding the human readable telemetry. With each vendor requiring unique telemetry data to debug implementation specific issues, do you foresee a requirement to standardize human readable telemetry? And then if so, if yes, then does it make more sense to drive this standard through OCP or NVMe? And any other thoughts on human readable telemetry? I think Vineet, especially that might be for you.
Yeah, I'll take the first part of the question and I'll defer the last part to Ross to answer in more detail. I think there is just to highlight a bit, there's a twofold problem with today's telemetry being encrypted. The first one is just the scale. When tens of thousands of drives which fail in a data center, it is just impossible to capture even the telemetry information today, which is encrypted, send it to the vendor, and the vendor is going to take its own time before it tells us the first level debug of what's wrong in the drive. So we need to speed that whole thing up and the goal is by having a human readable log information, we at hyperscalers should be able to debug what's going on wrong with the drive just at the first level. The second is the privacy problem. As we keep focusing more and more privacy, at some point it is just going to be impossible to share a lot of these encrypted information back to the vendors. So that's the twofold problem which we need to solve. So it kind of answers my question that yes, we need to get to the standardization of a human readable log, which can help us debug at least the first level information of is the drive in the healthy state or not. Now, whether to be done in an OCP or NVMe, I'll let Ross answer that. Ross, go ahead.
Well, Lee, you might have some opinions on this topic. Do you want to offer any opinions?
Sure. We take security very, very seriously in Azure because obviously it's customer data. And so with that, there is a mandate that no binary data can leave the data center ever. And so to be able to debug the device, as Neat says, debug at scale, that it doesn't have to be English text, but at least we need the decoder ring so that we know exactly what it is before we can send that on to the vendor externally. And obviously, if there are things, there's certain low-hanging fruit around how we can, standardize some of the things like, hey, what about a trace log? Can we standardize how a trace log is put together so that when you dump that in telemetry, we know what's there, and we can say that, hey, it's good to go ahead and give that to you guys to debug what the issue is. Panic IDs and very fine grain assert messages, things like that are all great ways to be able to do this in a way that gets around that whole binary issue. Where it gets standardized, NVMe OCP, I don't think it really, strongly matters to me which way. It's just that we need to have a decoder ring for all of that stuff.
Very good, thank you. All right, one last question. So with the emergence of persistent memory and fast storage devices, memory mapped IO is used to access such devices. So memory mapped IO in the past was used for read heavy workloads. Do you believe memory mapped IO will need to adapt for other kinds of workloads? And start us off with Matt here.
Yeah, I definitely think that there's going to be some adaptations. I don't think it's necessarily going to be in the storage device, because I, for one, would not trust a storage device to based on NAND to adapt to the memory mapped writes. Right, the application's going to have to deal with that sort of thing. Now with something like 3D XPoint, the media is able to adapt very well to taking random writes in a memory mapped mode. So there's going to be a variety of things I believe that have to happen, but I definitely think that's we're going to see more and more workloads start to move into this kind of semi-memory mapped operation.
Right. And to your point, I think in your presentation too, CXL and some of those standards will help with some of that as well.
Right.
Yeah, very good. Anyone else want to take that question?
Yeah, I think, persistent memory in the memory channel is awesome for doing a memory mapped IO, of course, right? Because especially in the systems we put together, the DAX ability within Windows, it's a true zero copy. You're doing load stores directly to that physical memory address in that persistent memory. As you start to then abstract that, going back to, hey, it's actually doing something over the NVMe and over PCI bus or other buses, the paradigm gets a little bit weaker. But it's, especially if you're using a very fast device, i.e. like a 3D XPoint type media device, it does have some very interesting wins to help out using memory mapped, and it also then starts to harden your software as you move forward into a persistent memory type environment.
Very good. Well, I think we're at our time here. Thank you so much, everybody, for joining us. Thank you, panelists, esteemed panelists. Appreciate it. Thank you for the time. Thank you for the great presentations this morning. And everyone, enjoy Flash Memory Summit. Thank you very much. Talk to you later.
Thanks, Jonathan.
Everyone.
Thank you.
Thanks, Jonathan. Thank you.
Thank you.